And so originally the plan was to review today because you were going to have a midterm tomorrow, but obviously you're not. So we're going to move forward. We'll talk about continuity and derivatives today. And then next Tuesday before your exam, we'll review. Can we go over some of the practice midterm questions? Sure, we can definitely do that. Let me, oh, did I not bring them with me? That was really dumb of me if I didn't. Should have. Oh, no, they're all right here. Cool. I think, yeah. Yes, I think I will have them. Yeah, we can definitely look at a couple of those. Do D and E on exam 2. Yeah, we can. Let me grab this. I'm going to go over a couple continuity questions first. Then we'll look at your questions, Lila, and then we will look at. We'll start talking about the limit definition of the derivative because it's definitely something that is probably going to be talked about in class tomorrow, I would imagine. So let me make sure that's on exam 2 and exam 3. Okay, there's 3. 1, 2. I'm assuming you mean the limit questions, Lila, because those are the only ones that have, I think, that's part D and E, right? Yeah, cool. All right. Yeah. Double check. Oh, sure, yeah, sure. And just a couple comments about the exam. So in case you hadn't, if you haven't looked into the practice exams, I highly encourage you to. She also posted something about like the exam, which I forget what she called it, like basically what to expect on the exam. And it's pretty much the same format. It's like one question that's like a continuity question, and then like 7 limit questions, and then a couple other things. But like you should definitely look at as much of the practice exams as you can before actual exam next Wednesday, because I imagine the format will be identical and the content will be very, very similar to what has already been posted. So all of you should definitely look at all the practice exams when you have a chance to, because I think it's good content. Come on in. All right, so let's look at this problem first though. So this question says, where is f of x equal to this piecewise function continuous? And we've got the piecewise function is 6 over x plus 2 plus e to the 5x when x is less than 0, 4 cosine of pi x when x is between 0 and 1, and x to the 17th plus the cube root of x plus 6 when x is larger than 1. So whenever you have a piecewise function like this, before you do anything else, you first want to check the individual pieces. So first, check the individual pieces. And I would point out that that first piece, 6 over x plus 2 plus e to the 5x, definitely is not continuous where? What's the problem there? Right, -2 is a big problem. And so now you need to check the point, and then you need to make sure that it's in that piece's domain. So this function is not continuous at x equal to -2. And since this is the portion where x is less than 0, that actually is a place where it's discontinuous. On the other hand, if this function was defined like to be this piece when x was bigger than 0, and this piece when x was like less than, switch it around like that, then it wouldn't be a problem because it wouldn't be in the domain. So got that. Anything else? No. 4 cosine of pi x is continuous everywhere. And x to the 17th plus the cube root of x plus 6 is also continuous everywhere. An odd root doesn't have any continuity issues. Only even roots do. So x equals -2 is certainly a place where this function is discontinuous. Now we need to check the places where we've switched from one function to the next function, or from one piece to the next piece, I should say. So we need to look at specifically x equals 0 when we go from this piece to that piece, and x equals 1 when we go from that piece to that piece. So for x equals 0, we're going to check the 3 things to see if it's continuous or not. Thing 1, does f of 0 exist? And if so, what is it? Well, I have to use the piece where x is equal to 0, so I'm going to plug in here. So I'm going to get 4 times cosine of pi times 0. Pi times 0 is 0. Cosine of 0 is 1. 4 times 1 is 4. It does seem to me like she's very likely to ask you to do some sort of trig evaluation, right? They're definitely trig on these practice exams, so be prepared for that. Thing 2, I have to look at the limit. certain, and since the piecewise function like this, we probably have to look at the two-sided limit from the left and from the right. Limit as x approaches 0 from the right of f of x is going to be the limit as x approaches 0 from the right, using the same piece, because that same piece is where x is greater than 0. And using that same piece, we're going to get the same result. X goes to 0, you plug it in, you get 4 times cosine of 0, which is 4 times 1, which is 4. Here's where things might fall apart. Really limit as x approaches 0 from the left. Well, now I'm using this piece of the function right here. I'm using the limit as x approaches 0 from the left of 6 over x plus 2 plus e to the 5x. And I'm just going to plug in 0 because whenever we're trying to evaluate a limit, the first thing we should do is just try to plug it in and see if we get a real number. If I do that, I'm going to get 6 over 2 plus e to the 5 times 0, but that's 3 plus 1, which is 4. The limit exists, it's equal to 4. The function exists, it's equal to 4. So yeah, this function is continuous at 0. So f of x is continuous at x equal to 0. And if someone's asked a question like this, where you've got kind of two breaks like this, hers are a little different on the practice test because hers is usually like the middle part is where x is just equal to a number. So it's a little different. But in this kind of question, I would be very, very surprised if it was continuous at 1 as well. Well, let's find out. So let's check at 1. So over here, we'll go over here. X equals 1. So now we're going to do the same sort of thing. We're going to check all three things. So thing 1, what's f of 1? Well, it's 4 times cosine of pi times 1. Pi times 1 is pi. Cosine of pi is -1. 4 times -1 is -4. I do like saying well, I guess I like being thorough. So part 2, does the limit exist? We know the limit using this middle piece will be the same, right? It's the same function. So here, if I looked at the limit as x approaches 1 from the left-hand side, which is the left side of 1, we're going to use that piece, and we're for sure going to get the same value. The question is the right-hand side the same? The limit as x approaches 1 from the right, well, now we have to use this piece of the function. X to the 17th plus the cube root of x plus 6. And we plug in 1, we're definitely not going to get 4 or -4. We're going to get 1 plus 1 plus 6, which is 8. Okay, so those aren't the same. That means this function is not continuous at x equal to 1. I usually like to be a little bit more thorough and say why it's not continuous at x equal to 1, because the limit as x approaches 1 does not exist. The left-hand limit and the right-hand limit are not matching up. You probably don't need to actually say that. I like to say that when I'm talking about why a limit doesn't exist or when a function is not continuous. Yeah, what's your name, by the way? Christian, what's up? Yes. Well, so when I plug in 1, and I should have written one more step here, I get 4 times cosine of pi times 1. Cosine of pi is -1, and 4 times -1 is giving me the -4. Cool. So then, notably, I have focused on where this function is not continuous because that is the easier question to first answer. Now that we know it's not continuous at -2 and at +1, we're going to now state where it is continuous, which is literally everywhere else. So we're going to say it's continuous on the interval from -infinity to, I don't want -2, union, I want everything from -2 up to, I also don't want +1, and then everything to infinity. So literally every value of x except for -2 and +1. Teresa. Sure. So whenever what's the first thing we do when we try to evaluate a limit? We just sub in whatever x is approaching. So what I did here, let me show this in pen so you can see it a little bit better, is I just said, well, if I plug in 1, I get 1 to the 17th power plus the cube root of 1 plus 6. But 1 to any power is 1. So I really have 1 plus 1 plus 6, which is 8. Excuse me. Typically, when you're asked on it, and you will be asked a question like this, or maybe not exactly like this on your first midterm next week, you will be asked to determine where it's continuous. And you'll have to look at each piece individually and see if you have any discontinuities there. And then you'll also have to look at basically where the piecewise function changes from one piece to the next, because that is also a place where it's probably going to be discontinuous. Other questions about this one before we move on to a similar but different example? Yeah, Dana. Yeah. It's not exactly the domain. The domain is a good starting place, but the thing is, this. So I actually, you know what? I meant to be more. Well, let's do one more like this. But I will point out here that the domain of this function is not quite the same as the where it's continuous, because the domain definitely includes the value of 1. So the domain here would be everything from negative infinity, -2, union, -2 to infinity. 1 for sure is in the domain. It's just not a very nice looking thing. Let's do another one though, because I have another one kind of in the back of my mind that is more similar to her first practice exam question, or any of the first questions on the practice exam. And actually I want to talk about that too, because I want to talk about how I would encourage you to attack that problem. Let me just, where did I put you? I had you, where'd you go? Did I leave you behind? I had one all ready to go. Might not have brought it with me because I was, oh, there we go. There we go. I found it. Okay, cool. So let's look at this one, and we're going to do kind of all the things here. Don't worry, Lila, we'll get there eventually, I promise. So let's look at this function of x equal to e to the x when x is less than 0, 3 when x is equal to 0, and 4 over x minus 2 squared when x is greater than 0. And we'll do this one like her test question. And here's what I want to say about this. If I were doing this as a test question, or really any kind of question, I wouldn't do the graph first, unless I was really good at graphing. I would say, like, I'm going to skip the graph for a minute, and I'm going to talk about the other stuff. So I'm going to talk about the limits first. So let's first find the limit from each direction. So let's do the limit as x approaches 0 from the right, and the limit as x approaches 0 from the left, and the limit as x approaches 0 overall. Now, on this question, on your practice exam or on your actual exam, I would encourage you, if this is written here, which it probably will be, I would say, okay, I'm going to write, well, that limit is equal to the limit as x approaches 0 from the right. Which piece do I need to use? The top, the middle, or the bottom? I'm approaching 0 from the right side of 0. Everybody. The bottom, right? That's where x is bigger than or right of 0. So I would literally rewrite this as the limit as x approaches 0 of 4 over x minus 2 squared. I think that is the thing your teacher would like to see the most. And then plug in 0. If I plug in 0, I'm going to get 4 over 0 minus 2 squared. I will point out we're actually plugging in 0, not like a number a little bit bigger than 0, actually 0. And then if I get this, 0 minus 2 squared is negative 2 squared, which is 4. So you get 4 over 4, which is 1. Great. Now let's do it for the other side. So if I'm approaching 0 from the left, I'm going to rewrite, and you really do want to write the limit. You need that limit still. Limit as x approaches 0 from the left. Now, which piece are we using if we were on the left side of 0? The top, the e to the x. Plug in 0, you get e to the 0, and e to the 0 is 1. And since these are the same, which I don't think they are ever on her practice exams, but I made up a different problem. Since they're the same, the limit is equal to 1. I don't think there's really anything else to write here. If these are the same, you're going to write this value. If these are different, you're going to say that this limit doesn't exist. Because for the limit to exist, the left and right hand side have to match up and be the same value. Cool. Questions? All right, part 2. What's the domain? Well, looking at each piece, e to the x is defined everywhere, right? There is no place where e to the x is undefined. 3 also defined everywhere. I mean, literally, there's nowhere to plug in x, so you don't have to worry. But 4 over x minus 2 squared, 4 over x minus 2 squared is undefined when x is equal to 2. And that is part of where x is greater than 0. So we need to exclude x equal to 2. So our domain is going to be everything but that. Now, range, I would probably skip until I graph it. Yeah, Dan. Mm-hmm. Okay. Yeah. Mm-hmm. Yeah. Sure. I'll address that in a minute, but give me a second. So here I'll point out that we only are getting x not equal to 2 because that's the only problem, and definitely 2 is in this domain. So for sure 2 is not okay. Everything else is totally fine. As I was saying, if you do have to find the range, I would wait until we've graphed it. But let's talk about the continuity before we talk about the range. So for continuity, where is this function continuous? Well, without a doubt, 100% for sure, where is this function definitely discontinuous? Everybody show me on your fingers, where is this function discontinuous? I mean, you're right as well, but I'm looking for the answer that's like right there. 2, right? Because it's not defined at 2. So we know without a doubt, anything that's not in the domain cannot be a place where the function is continuous. Because to be continuous somewhere, it would be defined there. This function isn't defined at 2. So it can't be continuous 2. So for sure, not 2. But then also, we better check out 0. Because although the limit exists at 0, it's not equal to the function value. Also not 0. Because the limit as x approaches 0 is 1, but f of 0 is 3. And those aren't the same. So if the limit exists, great. The function exists, great. But if they're not equal to each other, we don't get continuity at that point. So this function is continuous on the interval negative infinity up to 0, and then 0 to 2, and then 2 to infinity. And usually with this kind of question, the interval where it's continuous is going to have less than the interval where it's defined, or less than the domain. You can't ever have points where it's continuous that are not in the domain. Impossible. Okay, let's now address the graphing and the other part, the range part. So I'm going to graph this. What I really would encourage you to do is think about what each of these functions look like. I know that e to the x looks like this. I know that 3, I don't even want to graph 3 really, because I'm really only getting about 1 point when x equals 0 and y equals 3. You could graph the horizontal line y equals 3, but you only get it at the one time when x is 0, so it doesn't feel like we need to actually graph that. And then 4 over x minus 2 squared has a vertical asymptote at 2, and it's always positive, right? 4 is positive, x minus 2 squared is always positive. So I'm going to think about, well, I know that if I plug in 0, I get 1. I literally did it over here. It's going to look something like this. And this point here would be 0, 1. This point here would be 0, 1. But now I really only want e to the x to the left of 0, which is all this. And I really want 4 over x minus 2 squared to the right of 0, which is all of this. My piecewise graph is going to look like those two things put together. And then additionally, when X is 0, the Y value is going to be 3. Let's see if I think I can squeeze this in over here. So here's e to the x to the left, and I'm going to have a hole at 0, 1. Look like that. And then to the right, I'm still going to have a value of 1 because those graphs did have a meetup there. They were approaching 1, but now I'm going to have my vertical asymptote at 2. Let's do something like this. It kind of looks the same almost. It's not the same. I didn't mean it. I didn't mean for it to look the same. It just kind of happens to. And then I also have the point 0, 3. Yeah. So we don't have an asymptote at 4. We have an asymptote at 2. We have a vertical asymptote when x equals 2. Cool. Something else I was going to say here. Oh, so this is what the graph looks like. There's not really much more to say about it, I don't think. I wish I had left myself a little more room here. The other thing I'll point out is that now we can talk about the range. So how low do my y values go? Almost 0. We don't quite ever get to 0 though. And do I miss any values going up to infinity? Maybe 1, but I don't actually miss 1 because I get it somewhere over here. So we're getting everything from 0 exclusive to infinity exclusive. But really, more generally, you're just going to be looking at the graph to figure out what the range looks like, which is why I think it's probably worthwhile to do the domain before you talk about graphing the graph, I think. Right, you don't have to do the questions in order on the exam. You do them in whatever order you want. No one's going to be like, do this one first, do this one next. So I wouldn't do the graph right away personally. We come back to Dana's question. So I remember which one that was. I know I've got it right here. 1 second. Let me grab it so I can. Yeah, this one's cool. So this question says, consider this piecewise function. Let's zoom in a little bit here. Let me keep my notes in order here just so I don't get too out of whack. I've got papers everywhere. I'll be able to organize this later. Cool. Okay, cool. So this one says, consider this piecewise function. F of x equal to 1 over x plus 5 when x is less than 0, x equal to 2 when x equals 0, and square root of x when x is greater than 0. So when we look at this, we can only consider each piece on its own domain. So you're totally right. Square root of x isn't defined when x is negative. But we're only defining f of x to equal, the square root of x when x is already greater than. So what we're saying is this function, f of x, is equal to 1 over x plus 5 when x is less than 0. So for this piece, we have to exclude x equal to -5, right? Definitely x can't equal -5 because that would give us division by 0. And bless you. And then for the second part, x equals, or the function equals 2 when x equals 0. Well, there's no problems there. And then thirdly, the function equals the square root of x only when x is already greater than 0. Well, there's no problems there either, because if x is greater than 0, we can definitely take the square root of x. So here, the only issue is x can't be -5. So our domain is everything but -5. Negative infinity up to -5, union -5 up to infinity. The thing is, when you pick, so when we're setting x to equal a negative number, we're not plugging it into the square root part, we're plugging it into the 1 over x plus 5. And that's totally fine, no matter what x is, as long as it's not -5. That kind of clarify things? Cool. All right. Let's look at one more other continuity question. And then we will, and then we'll look at those questions that Lila. So the other continuity question I want you all to see, just because it's because we were talking about continuity last time, and also because something similar is on your actual practice exams, and I assume will come up on your actual exam, is something like the following. Where'd you go? Sorry, I'm got questions all over the place here. There we go. Determine what values of A and B make the following function continuous. And the function is f of x equal to piecewise function ax plus 1 when x is less than 2. Ax squared plus b when x is between 2 and 3. And negative 5 times b when x is bigger than 3. Notably, each of these pieces are continuous on their own domains. Because that first piece is what kind of graph is ax plus 1 if a is like a real positive number or a real negative number? It's definitely linear. It's a line, and lines are continuous everywhere. What about this second piece here, ax squared plus b? What kind of graph is that going to have? Right, it's a parabola, which is continuous everywhere. And this last one is just going to be a constant function, which is continuous everywhere. So each of these pieces on their own is already continuous on its domain, as are most elementary functions. They are continuous on their domains. The only thing we have to worry about is what's happening at 2 and what's happening at 3. So let me show you the way I think you should do this. Oh, I don't know. I don't know what your teacher actually expects. So yeah. Yep, that says x is greater than 3. Yeah, not equal to. I started to accidentally make the equal to part, and I was trying to like cover it up. And this x is strictly greater than 3. So let me show you actually both ways depending on. So I know that we need it to be continuous at 2. So to be continuous at 2, we need the limit to exist. We need the limit as x approaches 2 from the left, which is going to use this part here when x is less than 2. We need that to equal the limit as x approaches 2 from the right, which we're going to use this second part here, ax squared plus b. And then when I calculate those limits, I'm literally just going to plug in 2. So when I plug in 2 for x, I get 2 times a plus 1. When I plug in 2 for x, I get 4 times a plus b. And that doesn't tell me what a or b is yet. So I'm going to move on to the other equation. Now, what people really often do here is instead of writing out these limits, they just plug in the value. So you will see, like for this next one, people will often just plug in x equal to 3. And then double check. Yeah, okay, that's weird. But yeah. So for this other part, if I also need to be continuous at x equal to 3, I need the limit to exist at 3. So some people just jump straight to saying, I'm going to say, well, if I plug in 3 here, I can't. I have to write it. Sorry. Limit as x approaches 3 from the left. Left of 3, I'm using this piece here. So I've got ax squared plus b. I'm plugging in 3, I'm getting 9a plus b. And that needs to equal the limit as x approaches 3 from the right. What do I get when I approach 3 from the right? When I plug in x equal to 3, what do I get? It feels like it shouldn't be a hard question, but it feels like it actually is. You just get, well, no, there's nowhere to plug in 3 for x. So we get what we already have, negative 5b. Whenever you take the limit of a constant, you always get that constant back. It's kind of like saying, what's the limit as x approaches 17 of 2? It's 2. It doesn't matter what x is approaching. If your function's always 2, your function's always 2. Okay, so now we need these to equal as well. So we need that 9a plus b is equal to negative 5b. And now we have a system with two equations and two unknowns, and we can solve for them. So I might isolate B here. So subtracting 4a, I have negative 2a plus 1 is equal to b. And then I'm going to take that b here and substitute it over here. So over here I have 9a equals negative 6b. If I plug that in, I'm going to get 9a equal to negative 6 times negative 2a plus 1. And now I can solve for a. So let's see here. So I get 9a equals negative 6 times negative 2 is positive 12a. And negative 6 times 1 is negative 6. Subtract 12a, negative 3a equals negative 6, and then divide by negative 3, a equals positive 2. And then plug back in 2 over here for a. If a equals 2, we're going to get negative 2 times 2 plus 1 is equal to b, or negative 3 is equal to b. And that is a pretty standard way of approaching a problem like this. We know it has to be continuous, which means these parts have to match up when x is 2, and these parts have to match up when x is 3. Question. So when you see, and I think there is, I mean, just looking at your praxis exams, there's like a million up here. I think it's like the last, yeah, like the last question on the exam, very similar. You got the same kind of idea, right? Looking at that, you would say, okay, well, these two pieces have to match up when x is negative 1. So you're going to get negative a plus 3 equal to 1. You can solve for a, right? Fine. Let's just do this. So at negative 1, we're going to get a times negative 1 plus 3 equals negative 1 squared. And when x equals 5, well, these have to match up when x equals 5. So you're going to get 5 squared equals e to the 2 times 5 minus b. Now, I don't love writing this. I really feel like I should have first written this. The limit as x approaches negative 1 from the left of a times x plus 3 equals the limit as x approaches negative 1 from the right of x squared. I don't know if your teacher requires you to write this step first, or if you can just jump straight to that. You should look at her solutions and see what she's done, or even ask her in class. Do you, like, if you're solving for problem 6, do you expect us to write some limits and say they're equal to each other? Or can we just be like, yeah, I know when x is negative 1, this piece and this piece have to match up. I don't know what she wants. In either event, solving this, we end up getting negative a plus 3 equals 1. So negative a equals negative 2. So a equals 2. And over here we get 25 equal to e to the 10th minus b. So I would probably add b and get 25 plus b equals e to the 10th, or b equals e to the 10th minus 25. And that's it. That's all you can do. That's all you have to do. Yeah. Okay. So let me get to those questions. I gotten those tests out and I totally misplaced them. Sorry, one second here. This one, so you said 2 and 3. Let me check. Yeah, 2 and 3. That's 3. That should be 2. Wait, maybe 2. Nope, you're 1. Okay. So D and E. So problem, the limit problems, looking at D and E on question on midterms 2 and 3. Sorry. Yeah, there we go. Problem 3. Problem 3, D. Yeah, I figured that's okay, sure. So here is, and these ones, yeah, I don't love these ones, but they're not bad questions. So here's 3D from midterm. Sorry, I keep losing my spot here. From midterm 2, practice midterm 2, which is the limit as n goes to infinity of negative e to the n over negative 2 to the n. Okay, when you have this kind of problem, there's like 3 things that can happen. There's like a bunch of ways you can look at it. So here's what I would suggest personally. I don't love this negative 2 to the nth power. I would rewrite it like this. limit as n goes to infinity of negative e to the n over negative 1 to the n times 2 to the n. The negative 1 to the n matters, but not until the end. Maybe matters. I don't really care about it. I'm going to focus specifically on these pieces here. So let's ask ourselves a question. Which base is bigger? Is E bigger or is 2 bigger? E is bigger. E is like 2.7. I don't really care. I just care that it's bigger than 2 or bigger than whatever number is down. So now that means this fraction is getting larger and larger and larger because the numerator is getting bigger than the denominator. So this thing, normally I would say if I just look at the red parts, that thing is blowing up to infinity. But now we have to consider the fact that this thing is alternating in sign every time our value of n changes from an even number to an odd number to an even number to an odd number. So this thing is alternating back and forth between ever growing larger negative numbers and larger positive numbers, and larger negative and larger positive. So this thing, this limit does not exist because it's going to infinity, but it's alternating. It's going to an alternating infinity. But that doesn't exist. If you want to get a little bit more specific about this, you might say something like this. You might say this is the limit as n goes to infinity of negative 1, if you like, or just negative, over negative 1 to the n times e over 2 to the nth power. That might be better for you. You might be like, oh, I know that e over 2 is a number that's larger than 1. And when you keep multiplying a number that's larger than 1 by itself over and over and over and over again, it's going to grow larger and larger and larger. Even if it starts off like, you can start with 1.00000001 and keep multiplying it by itself over again. If you do it on a calculator, if you just keep hitting enter for a while, it's going to grow excessively large, even though you're starting off with a number very close to 1. Well, yes, but let's look at another example. Let's say we have the limit as n goes to infinity of 4 to the n minus 2 over pi to the n plus 1. First and foremost, the plus or minus 2 net 1 part, that's garbage. We don't care about that at all. So what I would encourage you all to do first is break those parts off. Say, well, really, I have 4 to the n times 4 to the minus 2 over pi to the n times pi to the 1. This part here doesn't really matter. That part there is just a constant. So really what I have is the limit as n goes to infinity of, I'm going to write this part first just because it's annoying me. And then 4 to the n over pi to the n, I could write as one fraction, 4 over pi to the n. Now let me ask you all, what's bigger, 4 or pi? You're like, I don't want to say it, but it's 4. It's 4, right? Pi is like 3 point something. So is this number getting larger and larger and larger? Yes, it is. And it's not oscillating. It's not alternating between positive and negative. So I will tell you, this limit does not exist. It's true. This limit doesn't exist. What number is it getting closer to? That's not a number. That's the answer we're going to write down. But infinity is not a number. So I will point out that we're going to say this limit is infinity. But you should all know that when we say a limit's infinity, we mean a lot. We mean this limit doesn't actually exist. This sequence or function or expression is not getting close to any one real number. But we have decided to be kind and be more informative with our answer. We're going to say, oh, even though we know this limit doesn't exist, I'm going to let the person know that I know that this function is getting infinitely large. So we're going to say that this limit is infinity, which really means the limit doesn't exist, but the sequence or the function just gets larger and larger and larger as you let n get larger. Does this limit exist? No. but we're going to say it's infinity because we want to give more information. Right. The other one doesn't get infinitely large. It gets infinitely large every other term and negatively infinitely large every other term. So we can't, you're right, we can't say that. And just to do the flip side of all these, if the denominator is something that's larger, it doesn't matter if it's alternating or not. So for example, if we take the limit as n goes to infinity of say like -3 to the n plus 1 over, I don't know, pi to the n. Well, I can see that I don't really pay attention to the alternating part. 3 is less than pi. So this denominator is going to grow faster. This limit's going to be 0. If you like, you can do this. I like to break up my negative thing to a power as -1 to that power times 3 to that power. And then I might break this up one more step as -1 to the n plus 1. That just means it's alternating. And then 3 to the n plus 1 is 3 to the 1 times 3 to the n. And this is all that really matters. 3 to the n over pi to the n, as n gets really, really large, that number is going to get super duper small because 3 over pi is a number that's less than 1. And you keep multiplying a thing that's less than 1 by itself over and over, the fraction gets smaller and smaller and smaller. So this limit is going to be 0. And it doesn't matter that it's alternating, because if you're alternating back and forth between numbers that are a little bit bigger than 0 and a little bit smaller than 0, they're still both getting closer and closer. In fact, 0 is the only number that an alternating sequence can converge to or have a limit that's equal to. Question, Dana? No, cool, okay. And then if it's alternating or not, if the top is smaller than the bottom, it's going to also converge to. So we could also say like the limit is n goes to infinity of, I don't know, 2 to the n over 3 to the n plus 2. That's going to be the limit as n goes to infinity of say 2 to the n over 3 squared times 3 to the n. And then this is all that matters. That's the limit as n goes to infinity of 1 over 3 squared times 2/3 to the n. Oh yeah, that thing is getting smaller and smaller and smaller the bigger you let n get. So that's going to be 0. If you have things like this where you have things raised to the nth power, whichever base is bigger is the one that's going to control what's happening. If the bigger base is in the denominator, the limit's going to be 0. The bigger base is in the numerator, you might get infinity if everything is positive. You might get a literal not existing if it's alternating back and forth between larger positive and larger negative. Okay. There are more though. Let's look at, I'm gonna save E for a second. I'm gonna look at the other test before I look at the, yeah. So I will point out question D on the other exam that you asked about is virtually the same kind of problem. Actually, I feel like that one's a little bit, no, that one's equally terrible, I would say. Here's the other one. Let me ask you all to think about this one for a second. Limit as n goes to infinity of -2 to the n plus 1 over 5. The 5 is kind of meaningless. So the question is, are we getting larger or are we getting smaller? I should say, ignoring the negative sign, are we getting larger or are we getting smaller? If n is really big, right. So I think this was, I think she was trying to trick you, right? She was like, oh, they're going to think there's a 5 to the n on there. That's just a 5. A 5 does nothing for us. So really, you just have like 2 to the n plus 1, which is getting large. But then, what's that going to do for us? It's going to alternate. So it's an alternating thing, getting larger and larger and larger, meaning the limit, right, not exist. Getting large. I might actually literally, like, if I was taking this test, I don't know what work I would show for this. So I'd be like, it's getting large and it alternates. So limit doesn't exist. There's my work. That's the work. I can't think to show really anything else other than that. Okay, and then we had E over here. Sure. Oh yeah, this one's cool. Limit as x approaches 3 from the left of x plus 3 over x minus 3. Okay, so this is what I would call a non-zero over zero type of limit. And when you have a not zero over zero, you have three options. Either the limit's going to be infinity, the limit's going to be negative infinity, or the limit's going to not exist. But specifically, if it's not zero over zero and it's a one-sided limit, it either has to be infinity or minus infinity. You only ever get the not existing if you have the left and the right side doing opposite infinity things. So the non-existing comes from, like, say you have like a vertical asymptote like this, where one side goes up and one side goes down. And then the two-sided limit doesn't exist. Each of those one-sided limits still exists. Well, each of those one-sided limits is still a thing that we say is a thing, either infinity or negative. It doesn't exist, but we say it's something. So, but then if someone has, so in fact, let's just do this one. Let's do this one all the way. So if I'm going to do this, I'm literally just going to plug it in. Here's the work I'm going to show. Plugging in 3, I'm going to get 6 on top. What am I getting on the bottom? 0. Okay, so if I'm getting 0 on the bottom, I'm going to delve a little deeper and say, am I getting a 0? Am I getting a number that's a little bit negative? A little bit negative, because my x is approaching a number that's x is approaching 3 from the less than 3 side, and then we're subtracting 3, so we're just a little bit negative. So I like to write this. I might, if I do this, emphasize the positivity of the numerator. So then I can say I have a positive divided by negative, which is overall going to be negative. Even though we know this limit doesn't exist, you still should write negative infinity. If you write does not exist, you will probably not get full credit. Or maybe any. Yeah. No. What I would say is, if you have a one-sided limit, if when you plug it in, you get a non-zero number divided by 0, then it's going to be, but it might not, but the left side doesn't always mean negative infinity. You actually have to check the sign. Let me show you the counter example. Let's say we had the limit as x approaches 4 from the left of 3 minus 2x over x minus 4. So now I'm going to do the same thing. I'm going to plug it in. When I plug it in, what do I get on top? Well, if I plug in 4, 3 minus 2 times 4 is 8. Negative 5. And a number a little bit less than 4 minus 4 is going to be slightly negative. And now we have a negative divided by negative, which is going to be positive infinity. So the side doesn't tell us whether it's going to be a negative or positive. It just tells us what's going to happen with the denominator. We still have to check kind of the overall sign to know if it's going to be positive or negative infinity. For this one here, looking at the other side, just to kind of fill in the blanks, we do limit x approaches 3 from the right of the same thing. Now we get a positive 6 over a slightly positive number. And then a positive divided by positive is positive infinity. And then if we were asked, we would say, oh, well, that means the limit as x approaches 3 can't exist because the right side and the left side are not the same thing. But we can't even say they don't exist in infinity or a negative infinity rate because they're not doing the same thing. They're doing this. Same deal actually over here. If you did the limit as x approaches 4 from the right of 3 minus 2x over 4 over x minus 4, you would still get negative 5 on top, but you get a slightly positive number on the bottom, and that would be negative infinity. So the overall double-sided limit here would also not exist. Just to kind of be thorough, here's one where they would exist. So let's say we have the limit as x approaches. Let's make it, no, let's not make it exciting, James. Let's say 2 from the left of 1 minus 3x over x minus 2 to the 4th. So we plug in 2. We get 1 minus 6 over a slightly negative or a slightly positive number raised to the 4th power. Or a question, better question, is the insides of this parentheses slightly negative or slightly positive? It's slightly negative, right? Because we're approaching 2 from the left. Now, the better question is, does it matter? And the answer is no, because when you raise something to an even power, it doesn't matter if it was negative or positive, it ends up being positive anyway. So here we're getting -5 over a slightly positive 0, which is negative infinity. And the same thing is going to be true when we approach 2 from the right-hand side. Because when we approach 2 from the right-hand side, we still get 1 minus 6 on top. And now we get a slightly positive number raised to the 4th power. So we still get -5 over a slightly positive number, which is negative. So then you could say the double-sided limit as x approaches 2 of 1 minus 3x over x minus 2 to the 4th is infinity. Meaning in this case, if you graph this thing, both of your vertical asymptotes, oh, negative, holy smokes, don't get rid of that. Both sides are going down like this. So the graph of this looks something like vertical asymptote of positive 2, and both sides are going down, 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 down. That's what we mean when we say that. Okay, there was one more question that was asked about, which was, yeah, that's a good one. Ooh, that's good, maybe not good, terrible, maybe more the answer. The E from one of these tests, I'll just write it out here. The limit as x approaches 0 of 1 over x times the square root of 1 plus x minus 1 over x. That's not too bad. If you plug in 0, you get 1 over 0 minus 1 over 0. Now the problem here is those are sorts of infinities. And infinity minus infinity is dicey. It's like 0 divided by 0. It literally is actually like 0 divided by 0. It is also what's called an indeterminate form. Really what that should say to us, when you have an indeterminate form, 0 over 0, infinity over infinity, infinity minus infinity, what that really means is you have to do more work. You have to do probably some algebra, or maybe something else. Here, if you're subtracting fractions, we should actually subtract fractions by getting it. So I'm going to rewrite this as the limit as x goes to 0 of 1 over, well, here I actually don't need anything more. I have an x in the denominator here, I have an x in the denominator here, I'm set. But for the minus 1 over x, I need to multiply that by the square root of 1 plus x over the square root of 1 plus x. Interesting. I'm not thrilled about where this is going, but that's all right. The limit as x goes to 0 of, I have 1 minus the square root of 1 plus x over x times the square root of 1 plus x. After you've done some algebra, it's usually a good time to check and see, can I plug in x going to 0? If you plug in 0 for x, what do you get on top? 0. What do you get on the bottom? Also 0. You get 0 times 1. 0 over 0 means, what does 0 over 0 mean? Thank you. Exactly. 0 over 0 means no, it is not 1. 0 over 0 is 17. Let's see. 0 divided by 0. Let's see. 17. 17 times 0. 0. Subtract. Yeah, that works. The point here really is, I'm not trying to make fun a little bit, but the point is that you can, the answer can be anything. But what it really means is you have to do something else. Because 0 over 0 literally can be any value. And there's a big reason, which we're going to talk about in the last 15 minutes here, that we talk about 0 over 0 a lot. We're about to see why this is such an important idea. Here, I would probably try multiplying by the conjugate. This seems like, and maybe that's not going to work, but it's probably, I don't know, I actually don't know. Let's try it. Let's multiply by 1 plus the square root of 1 plus x over 1 plus the square root of 1 plus x. So when we do that, the things that are conjugates, we do multiply out. We multiply out the top, you get 1 times 1, and then the middle terms cancel. I'm going to write them out this time just to make sure everyone sees it. So you get 1 times 1, you get 1 times the square root of 1 plus x. You get minus square root of 1 plus x times 1. And oh, be careful here. This is actually a place where it's really easy to make a mistake. You get minus the square root of 1 plus x times the square root of 1 plus x, which is minus the square root of 1 plus x squared. Now be careful here. I've just made a mistake. I didn't write parentheses around that whole thing that should be being subtracted. It should be minus parentheses 1 plus x. And then on the bottom, we don't multiply it out. We leave it as all this gross garbage. X times the square root of 1 plus x times 1 plus the square root of 1 plus x. And the reason we leave it like that and don't multiply it out is because specifically, we know that this x here, that x is a problem. It's making us divide by 0. We would like for it to cancel out. But there's no good reason to multiply it through everything else if we're trying to make it cancel out. We want to leave it factored out. So now we're going to simplify the top. These I never should have written in the first place. And I have the limit, as x goes to 0, of 1 minus 1 plus x is minus 1 minus x over x times the square root of 1 plus x times 1 plus the square root of 1 plus. It's kind of a gross problem. The ones cancel. And what's negative x divided by x? Right. So the negative x divided by x leaves us with a negative 1. And then you're left with the square root of 1 plus x times 1 plus the square root of 1 plus x. And now that we canceled the thing that was causing us a problem, it's probably a good time to check and see if we can plug in x equal to 0. If I substitute in 0 for x or plug it in, I get negative 1 over the square root of 1 plus 0 times 1 plus the square root of 1 plus 0. And that's going to work out. Okay, negative 1 over square root of 1 is 1 times 1 plus the square root of 1 is 1. And 1 times 2 is 2, so I get negative 1 over 2. That's kind of a lot. It's not a terrible problem, it's just there's a lot to do here. Questions about any of this particular problem? Okay, so as much as I would love to continue talking about the practice exams for the next 20 minutes, I should set you up for what's probably going to happen in class tomorrow. Definitely on Tuesday, we'll review as well. So the plan is Thursday, we'll probably talk more about limit definition of the derivative. Tuesday, we will for sure review for your exam that's going to be on Wednesday. I will probably try to write up some sort of additional practice again, not that you really need another one, but I would encourage all of you to, over the weekend or whenever you have time, look at each of these practice exams as much as you can. Give yourself, at least with one of them, give yourself 50 minutes. Sit down, take the exam like it's actually an exam. You get a calculator, then you don't get a calculator. So just, no resources, no solutions, no nothing. Take at least one of these tests like it's a test. Give yourself 50 minutes on your own, no distractions. And then you can grade it yourself. You can look at the solutions, or if you really want, you can scan it and email it to me and I will grade it for you. Yeah, I can do that. I'm going to be out of time this weekend, but it's all right. I can still do it. So yeah, but definitely at least take one to make sure because the format is the format, right? Your test is going to look not identical to one of these tests, but virtually identical, right? It's going to be the same 6, 7, 8 pages, whatever, of the same types of questions, just different limits, different functions, but really the same content. So do yourself a favor and practice at least one as an actual exam. I can't recommend it enough. Okay, and then Tuesday we'll review, but for now, let's talk about, where'd you go? Where'd you go? Not you, yeah. Let's talk about derivatives. So let's look at this example first. Let's find the average rate of change of f of x equal to x squared plus 6x on the interval from 1 to 3. By the way, we're going to use this a lot, so I'm just going to abbreviate average rate of change like that. Oops, sorry. Okay, so here's a vague idea of what this function looks like. Again, not perfect, but x squared plus 6x looks something, sure, kind of like this. It continues on this way. Okay, and here's 1, and here's 3. When you're trying to find the average rate of change, you're really trying to find the slope of the secant line that connects this point here to this point here. So the average rate of change is just equal to the slope of the secant line. Or in this case, it's equal to f of 3 minus f of 1, the difference in the y values, over 3 minus 1. So let's see. So that's going to be, I guess I could plot some points here. This is 3 comma f of 3. This is 1 comma f of 1. That's what I could find them. So f of 3 is going to be, let's see, 9 plus 6 times 3 is 18 to 27. It's 27 minus 1 plus 6 is 7 over 3 minus 1. That ends up being 20 over 2, which is 10. Okay, so the slope of that line is 10. Let's get a little bit closer. So if I plug in 3 squared plus 6 times 3. I was given 1 and 3 because I said I want to find the average rate of change on the interval 1, 3, or from 1 to 3. Let's ask the same question, but now on a smaller interval. Let's say you want to be on the interval 1, 2. Okay, same idea. We'll draw a little picture here. Same kind of function. But now I'm going from 1, 2. So now my average rate of change is going to be, well, still the difference in the y values divided by the difference in the x values. It's going to be f of 2 minus f of 1, 2 minus 1. Plugging in 2, I get 4 plus 12 is 16. F of 1 is still 7. 2 minus 1, that's going to be 9 over 1, is 9. So the slope of this line is a little bit less steep. This line, this secant line has a slope of 10. The secant line has a slope of 9. Let's get just a little bit closer to 1. Let's say we want to look at the interval from 1 to 1.5. So, okay, same idea. Same function looking like this. Whew, okay, getting kind of close here. When you get so close, it's kind of hard to draw the secant line. You can do it though. Wow, there's my secant line. And now the slope of my secant line, or the average rate of change, is going to be f of 3 halves minus f of 1 over 3 halves minus 1. So what was my function? My function was x squared plus 6x. So f of 3 halves is going to be 3 halves squared plus 6 times 3 halves, which is what, 9 fourths plus 18 halves. That's something. So 36 plus 9 is 45 fourths. This is going to be 45 fourths minus 7 over 3 halves minus 1. 7 is 28 fourths. So you get 45 fourths minus 28 fourths over 1/2. 45 minus 28 is 17. Yeah, 17. You get 17 fourths divided by 1/2 is like multiplying by 2. We end up getting 17 over 2, which is 8.5. So we started off with the slope of 10, then the slope of 9, then the slope of 8.5. We did it again, we might get a slope even smaller, even closer to 8. I'm guessing slope might be, or I should say, I'm guessing the slope of the tangent line might be 8. So here's what we're doing. We are really trying to answer the question, what's the slope of the line tangent to this function at the point x equal to 1? So the idea here is the following. Here's my function. It looks like this. And I would really, really, really like to know at 1, what's the slope of the tangent line? And the idea is that we're going to take the slope of a secant line and then take the limit of that slope until it gets closer and closer to being the slope of the tangent line. Here's how we do that. I'm going to say, well, I'm going to pick some other point over here and call it whatever the point I'm interested in plus a little bit. I'm going to say this is going to be 1 plus h. And the idea is to find the slope of the secant line between these 2 points, or also known as the average rate of change. The average rate of change between 1 and 1 plus h is going to be f of 1 plus h minus f of 1 all over 1 plus h minus 1. Or once again, right, that's the point 1 plus h comma f of 1 plus h. That's the point 1 comma f of 1. The difference in the y's divided by the difference in the x's, which is how we generally find slope. Reminding ourselves that our function is x squared plus 6x. I think, sorry, I forgot what it was. I believe that's what it was. Yeah. So my average rate of change between these 2 points is going to be a little bit gross, 1 plus h squared plus 6 times 1 plus h minus f of 1, which was 7, all over 1 plus h minus 1, which is just h. Now check this out. I'm going to simplify a bit here. 1 plus h squared is 1 plus 2h plus h squared. 6 times 1 plus h is 6 plus 6h. And now look. 1 plus 6 minus 7 cancels out. So we're left with 2h plus h squared plus 6h over h. Each of those terms has an h in it. We can factor out an h, and we're left with 2 plus h plus 6 all over h, and those cancel. So we're left with 8 plus h. So I want to point out, I know we're almost out. Oh, I got like 10 minutes. The slope between these 2 points is 8 plus h. And now here's the big idea. To find the slope, and this is the slope of the secant line. To find the slope of the tangent line, we're going to let h get closer and closer and closer to 0. And let this point get closer and closer and closer to that point. So the slope of the secant line is equal to 8 plus h. And the slope of the tangent line is equal to the limit as h approaches 0 of the slope of the secant line. Because we're letting those points get closer and closer together. We're letting the secant line get closer and closer and closer to being the tangent line. And that's going to equal, in this case, the limit as h goes to 0 of 8 plus h, which is just 8. This is really not the whole idea, but a lot of the idea of how we find the derivative of a function. Because one interpretation of the derivative of a function is the slope of the tangent line. The way we find the slope of the tangent line is we find the limit of the slope of the secant line. So here's the kind of general definition. The slope of the tangent line to y equal to f of x at the point a comma f of a is given by the limit as h approaches 0 of f of a plus h minus f of a all over a plus h. Again, reminding ourselves that this is the slope of the secant line, and we're taking the limit of that slope to get the slope of the tangent. Let's look at a couple of examples, which I have misplaced. That should be fine. So let's say we want to find the slope of the line tangent to y equal to the square root of x at the point where x equals 9. Which looks something like this. We would love to find the slope of that line that's tangent to this graph at the point 9, 3. So what we're going to do is we're going to say, well, slope of that line is going to be the limit h goes to 0 of f of 9 plus h minus f of 9 all over 9 plus h minus 9. And I should pause and draw a different picture here. But just to kind of make sure you guys are really seeing what I want you to see, the whole idea here is that we've got this square root function. Maybe here's where the point 9, 3 is. And here's some other point over here, 9 plus h, comma, the square root of 9 plus h. And we are finding the slope of the line between those 2 points. That's this right here. And then we're just letting this point get closer and closer and closer and closer to that point. If we do that, if 9 plus h is getting closer and closer to 9, that means h has to be getting closer and closer to 0. 9 plus something is only getting closer to 9 if this thing you're adding on is getting smaller and smaller and smaller. So to find the slope of the tangent line, we're saying, okay, creep a little bit in here and now find the slope of the secant line there. And then creep a little further in and find the slope of the secant line there. And just keep creeping closer and closer and closer until you're actually finding the slope of the tangent. This is why we have spent a decent amount of time talking about 0 over 0 types of limits. Because if you actually plugged in 0 for h, you would have a 0 over 0 type of limit. So looking back here, I've got the limit as h approaches 0 of the square root of 9 plus h minus the square root of 9 over 9 plus h minus 9, which is just h. Okay, I've got a square root limit here. I'm going to use the conjugate. So this is going to equal the limit as h goes to 0 of the square root of 9 plus h minus 3 over h times the conjugate, the square root of 9 plus h plus 3 over the square root of 9 plus h plus 3. Multiply out the conjugates. When you multiply out conjugates, you always just get the first thing squared minus the second thing squared. The middle terms always cancel. So you get 9 plus h minus 3 squared over h times the square root of 9 plus h plus 3. The 9's cancel. And h over h is just 1. So we're really left with the limit as h goes to 0 of 1 over the square root of 9 plus h plus 3. But now we can actually plug in 0 for the remaining h and get 1 over the square root of 9 plus 3, which is 1/6. Follow-up question. what is the equation of the line tangent to y equal to the square root of x at x equal to 9? And this question is usually relatively easy to answer if we've already done the first part. We know all we need. We know that the slope is what? Yeah. And we know that the point is, well, we've got x equal to 9 and y is the square root of 9, which is 3. And once you have a point and a slope, you can toss it into the point slope formula and say, okay, y minus the y coordinate equals my slope times x minus the x coordinate. And sometimes you can leave it like that. Sometimes they want you to solve for y. So you can write this as y equal to 3 plus 1/6 times x minus 1/6 times 9. And then you can simplify this and write it as 1/6 x. And 1/6 9 is really 9 over 6, which is 3 halves. And then 3 minus 3 halves is positive 3 halves. So plus 3 halves. So that would be the equation of your tangent line. So sometimes we like to find the equation of a tangent line at a particular point. But I will tell you, we don't do this very long. What we're really going to start doing is after we get tired of this, we say, well, instead of finding the slope of the tangent line at a particular point, let's just find the slope of the tangent line as a function of x. So more generally, the way we would find the slope of the tangent line here, or the derivative, we would say, well, f prime of x is going to equal the limit as h approaches 0. Instead of using 9 or 5 or whatever point you like, we're just going to use x. It's f of x plus h minus f of x over h. And then you find the general formula for the derivative, which is the slope of the tangent line. And then you can plug in whatever point you like. So this is kind of how we like to start. But then if we do it this way, we're going to say, well, that's the limit as h approaches 0 of the square root of x plus h minus the square root of x all over h. Then we'd multiply by the conjugate again. Multiplying it out, we're going to get the limit as h goes to 0. On top, we'll get x plus h minus x. On the bottom, we leave it alone. But that should be, I made a mistake. Did I multiply by the conjugate? No, I did not. That should be a plus there and a plus there. Sorry about that. And then that should be a plus there. X minus x cancels. H over h is 1. The limit as h goes to 0 of 1 over the square root of x plus h plus the square root of x, which ends up being, now we plug in 0 for h, 1 over the square root of x plus the square root of x, which is really 1 over 2 root x. And then you can say, oh, if I want to find the slope of the tangent line when x is 9, just plug in 9 for x, and oh, you get 1 over 2 times the square root of 9, which is 1 over 2 times 3, which is 1/6, which is what we got before. But you can also then say, well, what's the slope when x equals 16? Or other, right? This is a lot more general, and you can answer the question for any value of x as you want, as opposed to the one particular value of x we found. All right, I stopped talking. So on Thursday, we will talk more about the derivative and the limit definition of the derivative. And then on Tuesday, we'll move back and we'll go back and review for your midterm exam, which is on Wednesday. All right, good stuff. Take it easy.